Hello, everyone. Let's get started for tonight. For last day, we missed that class because I had some urgent matter to attend to. Sorry for that. And let's try to cover as much as possible tonight. We have like 2 days left. I hope to wrap up the theory part today and then do the final review next day. So that's what my plan is. So we have like 2 lectures left, or actually you're supposed to actually go through all these till the lecture 23 by this time. So let's see, on lecture 22, which is the last part of the cache memory 4, uh, and this lecture 23, which is a virtual memory. Do you have any specific topics, concern, question to ask on these two parts? Let me see if there is anything on the discussion board. No. Okay. So for the last part of this cache, which is cache memory 4, which has a lot of formula, you probably can feel scared, like that's okay. But the trick there is to grasp the concept. Okay, don't try to remember the formulas. Okay, try to grasp the underlying concept and how those formula came alive. So that's the way you should study that part. And given any problem around that part, just apply your common sense there. Okay, so apply your common sense, apply your understanding of different parts of those formulas and put them together. So there is nothing like rocket science about those formulas at all. One thing in those calculations, what I've seen student commonly mistake that instruction execution, if you are talking about the instruction execution, that always involve the memory access. Why? Because of the instruction fetch. At that stage, processor, no matter what type of instruction, it will fetch instruction from the memory, right? It's only for the memory bound instruction like load words, store words, like push, pop, those kind of instruction that basically go and grab these two memory access. One for in the instruction fetch, and another part is your memory, data memory part. Okay, so you need to make sure you got that understanding as well. The other part I want to mention is that, so there in the towards the end of that lecture 22, what we discussed about the set associativity to improve the cache performance. Now, is it always going to do improve the cache performance? No. What do you mean by that is that you might find an application which is not, whose performance is not being improved by this increase of associativity in the processor. Maybe it can actually go other way. So all this improvement of the cache performance, we are talking in a statistical sense. Like on average, like when we calculate the hit rate versus and miss rate, what that number, like 90% hit rate, 95% hit rate, that number is itself a statistic. Okay, so it runs different benchmark program and average out the gain in that improving performance. So that says that it may not applicable to one specific scenario. So that's what I want to mention with you. Okay, and then today's topic was the virtual memory. Virtual memory, in fact, is a big topic in operating system. Okay, so and I would always think studying the hardware aspect of the virtual memory should be taught in parallel with the software aspect of the virtual memory, what is being taught in the operating system class. So if you have already taken operating system class, or you are taking right now in parallel with computer architecture, if you're taking operating system class and you have came across this virtual memory topic, then probably you'd be more clear on this one-to-one relation between the concept we are studying here in the hardware level versus the concept that being taught in the operating system level. Now, if you haven't taken the operating system level, don't worry. Just remember this part, this understanding from the hardware perspective. And when you pick up the operating system, I would suggest to come back to this topic, just review for once that this one chapter, virtual memory chapter, hopefully with that, it will be much easier to grasp the concept on the software side, like why is something is done that way and what is not, etc. So that's my suggestion. Just if you haven't taken operating system yet, make sure you review at least this chapter to brush up your concept on the hardware side of the virtual memory. So this is mainly your memory management and other type of resource management that operating system does. This is like special management. Special management is your memory management, which means how it controls, operating system controls the resources and resources of memory and distribute among different process or different program being running on the system. That is the spatial management. And temporal management is that how it distribute the usage of the processing element, the core processor, with respect to different parallel program being running together. Nowadays, it is easier in the sense that your system already has like 4 core or 8 core. That means 4 or 8 independent program actually truly can go in parallel at the same time point. But in past, when there is only one core available on a computing system, still the operating system can elude user by showing as if it is running like 50 different programs at one time. How it does it? Basically, a software program has two parts of it. One is when it is using the processor, like it is crunching some number, computing something like scientific application, for example, they're all processor heavy program style. But nonetheless, there would be some part which would start reading from the disk or writing from the disk or reading to the memory or writing to the memory. So these are kind of an IO operation, memory operation. This is also a part of your program execution. So when a program comes into that stage where it is doing some memory access, read or write, disk or main memory, doesn't matter, some memory access, that time as a resource, your processor is freed up. And operating system can come in and schedule another process to use that resource, while the other process is busy in connecting in this memory access process. So this is, and also like there is a timeout concept when some this program, like it's a predefined in the ways, and probably some configuration you can control that which process take how much time. So if it goes out of that time, it goes into some sleep state and another process gets scheduled onto the processor for execution. So this part is called a context switching. So context switching is also part of your operating system class study. Now, what is here in this class is mainly the hardware support. What is the hardware support needed for operating system to implement this virtual memory? Okay. Virtual memory, in a principle, it gives the illusion to a programmer that it has a larger memory than actual main memory is installed. Okay, so, and also like in the sense that, let's say your laptop is like 16 gig laptop. So when you program, you never think that only my share is probably 1/10 of that, like 1.6 gig. You never think of that. You think that all 16 GB is available to you, and you can assume that as a programmer. But in reality, your laptop is actually running 50 different processes, and each needs some part of the memory, right? So physically, it is not possible to fit in all this 50 process onto the memory given 16 GB. But each process actually enjoy that entire 16 GB space, like as if that's the memory they're enjoying. So that is the concept of the virtual memory. That is gives the illusion. Okay. The main idea is very much similar to cache idea in the cache. Here, disk is a cache. Just imagine that your disk system is a cache. The term block, what we studied in the cache chapter, is here is called a page. What we studied as a miss in the miss concept of the miss in the cache, it's basically termed as a page fault. So concept wise, they're not very different with each other. Terms are different because of the fact the cache concept evolved in the hardware space, like people involved with the hardware, and that from that perspective, this cache memory system concept and implementation came in. Whereas the virtual memory system came from the software world, where it's basically trying to fit like many processes onto with a restricted amount of main memory. But concept-wise, they're same. They came from two different worlds. That's why you see these term differences, but underlying concept is practically the same concept. So with the since the the laptop or any modern system uses virtual memories, system with the solid state disk makes system much faster. You can actually if you have used both the traditional disk, the rotating electromechanical disk, that system versus a system having a solid state disk, you would probably felt a difference in the boot time. Like solid state devices boot almost instantaneously.
Professor?
uh, and your that's one part. So basically, since this solid state disk system gives performance benefit, much faster operation, that's the reason you will also feel that this page fault and other services are basically takes less amount of time. So your apparent average experience performance around the performance would be much better with a solid state disk system.
Professor?
Yes.
You said that having a lot of virtual memory makes the system faster, but isn't the isn't comparatively the hard drive much slower accessing it than accessing the RAM or even the cache?
So it's all it is just go back to the cache concept, right? In the cache, your RAM, the main memory, is much slower than the cache memory system. So it's mostly, it's basically in that process, it bringing in the block, and in hope that program will use that block from the cache over and over again because of this temporal locality and spatial locality, right? The same concept apply in this system too. Here, instead of block, we call it a page. A page is being transferred to the main memory. Okay, and it's hoping by the property of this spatial locality and temporal locality that that page residing in the main memory will be accessed frequently and repeatedly, and hoping that you don't need to replace the page with another very frequently. If that happens, then you'll see there is a slowdown. Make sense, Yurik?
Is that what thrashing is?
Was that?
That's what thrashing is, right?
Fraction, memory fraction
Oh
is,
no, thrashing, thrashing. When the when essentially the computer locks up because it's trying to read from the hard drive.
right. You will see, like, especially in the older system with the rotational disk, you'll see that there's disk spinning very rapidly. And you can actually, if you look at that resource monitor, Control-Alt-Del in the Windows system, resource monitor, you'll see the disk activity goes hayward. That's where it is servicing the page. It is writing back the page onto the disk and then reading back another page from the memory. And since your main memory is full with a lot of processes, probably they are infrequently doing this page service, and that's where your slowness comes up. So that's why probably you have observed, if you actually increase the size of the main memory, let's say your laptop had 8 GB and you have enough slot to insert another memory card to increase that to 16 GB, immediately your performance problem gone there, because there are less amount of page fault. Does that make sense, Lorik?
Yeah, thank you.
Okay. All right. So let's do a quick problem around this virtual memory. Okay, let me see. I'm just trying to find out the problem where it is. Okay, here we go. All right, let me share my screen with you. Okay, so this is the problem looks like. There is a 32-bit computing system, uses the virtual memory. Your page size is 4 kilobyte, and it uses 4-way associative cache. And that cache can hold 1 megabyte of information at a time with a block size of 1 kilobyte. So we have many different components of this problem. One is the page size, 4-way associativity. It holds total 1 megabyte of information, and block size is 1 kilobyte. For a memory access, both TLB and the cache access time is 1 nanosecond. So we access TLB to translate the address, virtual address to physical address, and then we access the cache, corresponding physical address, the cache. TLB miss rate is 25% with 20 microsecond penalty. And cache miss rate is 10% with 50 microsecond penalty. These are just some made up number, by the way. Page fault rate, let's say it's 0.01%. With the page service, that is bringing back the page from the disk to memory, is 1 second. Now, first problem is how much time would be spent for 1 million 10 to the power 6, that many memory access in second unit, up to the 3 decimal places, maybe. And then the next problem, given this memory configuration, we need to determine the tag, cache index, line index, block index for a virtual address these with a TLB entry, let's say given these to this. Okay, that means like you are already kind of given the part of the translation in this process. Okay, so TLB entry of this is this. You build up a physical memory, then break them up into tag, cache, and block index. So let's do this problem in a group, and let's take maybe about 15 minutes to discuss among ourselves, and then we'll have the discussion. Yeah, let me just quickly reassign 15 minutes. Okay, here it go. Okay, so anyone, any volunteer to discuss this problem? No? At least explain the approach. Okay, let me do it then. Let's see. So here in this problem, let's talk about this performance number or times, right? So as usual, I would like to start with ideal case, means there is no miss, nothing, right? So that means without no miss, either TLB miss or cache miss, doesn't matter. It is 1 million, right, multiplied by 2 nanosecond. So it is like 2 million nanosecond, which is nano micro, yeah, 0.002 second. Now why 2? Because this is like 1 nanosecond for TLB. Like it says that both TLB and cache access time is 1 nanosecond. So one is for TLB, another nanosecond for cache access. Now, then let's talk about a condition where there are like only cache miss, like no TLB miss but cache miss. That's an independent uh, phenomena. And for that, what we have seen, it says that your cache miss rate is 10% with 50 microsecond penalty. So that means we have 1 million access multiplied by 0.1, 10%, multiplied by 50 microseconds. So that many microseconds. So this is about 5 million microsecond, which is 5 seconds. Now let's talk about the TLB. Only, not TLB, like TLB miss, but no page fault. So what is that? That's basically your TLB miss is 25% penalty, 20 microsecond. So that means it is 0.25 multiplied by 20 microsecond, which comes about another 5 million microsecond, which is 5 second. So we have like different component. One is our TLB miss scenario. Another is our cache miss scenario. Another is like no miss. And now let's talk about if there are page fault, like my page service time. Page service time, so we calculate 1 million multiplied by 0.25 multiplied by 0.0001 multiplied by 1 second. So what is that about? This is, see, your page fault can occur if there is a TLB miss. If there is no TLB miss, that means the page are already in the uh, memory. Okay, and that's why we are multiplying the our miss rate. Like out of this 25%, which is has TLB miss, there is a 0.01% chance that it will go in a page fault mode. So this is become like, if we calculate that, that will become about 25 seconds. So which is kind of like, it's though they are the made up number, but it actually follows the general pattern that if there is a page fault, page service actually takes up chunk of the execution, like memory access time. Now I am saying execution time, memory access time. Then the cache miss is a 5 second, and TLB misses. But if there is no miss, then we are about really blazing fast. Okay, so now you add up the entire thing. So total time, total access time equals your 25 plus 5 plus 5 plus 0.002, which is 35.002 second. So far, so good. Any question?
Yeah, sorry, but what is the difference between the TLD miss rate and the page fault rate? What is the difference between the two?
Misread, you mean? What? Can you repeat the question?
What does it mean for the TLB to be missed versus the page to be missed? The page to have a fault.
So TLB to be missed means in your TLB table, translation loop aside buffer, that table, your corresponding page number is missing. It doesn't know how to translate from the page number like to the physical memory, physical page number, like virtual page number to physical page number. It doesn't have it. Then it goes into the page table in the main memory to retrieve that mapping, virtual mapping to the physical number mapping, physical page mapping, virtual page number to physical page number. So your page number inside the processor has two places. One is in the TLB, which is in the cache-like structure, which is only part of the page table being loaded there, but your process full page table is in the main memory. All right. So if the TLB miss happens, it goes into accessing the page full page table in the main memory, and if in that page table it indicates that corresponding page is not in the main memory but in the disk, that time the page fault occurs. Make sense, Yuri, so far?
Oh, okay. So the pages are located on the hard drive, but they get moved to the memory, to the RAM.
Right. So pages can be in either on the disk or RAM. Okay. So and
So when it's between the disk and the memory, then we talk about pages, and when it's between the memory and the cache, then we talk about blocks.
exactly.
Oh, okay. Thank you.
Okay. So I'm not sure if you have taken operating system class or not, but hopefully that part would be cleared up more from if you look from the operating system side, what is what. Right. But glad that you brought up this question. Now, okay, now the next problem. Let's move towards the next problem. So it's about the tag, cache line index, block index, etc., etc. Right. So this one, okay. Let me go to the next page. Okay. Okay. All right. Let me also copy that problem over here. Okay, so in this problem, we have, first of all, we can, uh, let's come from the cache perspective, right? So we have this block index, we have block size, right, somewhere. Let me see. Okay, the block size is 1 kilobyte. So from that, we can say that your number of block index, number of bits in block index is log base 2 of 1k, which is 10. Now this next data is, this is four-way associative cache with total 1 megabyte of information. So that means, first of all, we can conclude that total number of cache line is log base 2 of 1 meg, which is 20. Sorry, what I'm saying, my bad. Total number of cache line, it would be, we have like 2 to the, so 1 MB, 1 MB is 2 to the power 20, and block size is 1 KB, 2 to the power 10, which is 2 to the power 10, 1024. Now it is a four-way, since four-way set associative, div cache line index should be log base 2 of 1024 by 4, four-way associative. And 1024 by 4 is 256, which log base 2 is 8. Okay, so we calculate that one. So that means number of bits in tag 32 minus 10 from here, minus 8. So it is 22, 22 minus 8 is 40. So far so good, right? Now we have one more information, which is my page size. Okay. So page size is, says that 4 kilobyte, right? 4K. So that means number of bits in page index is log base 2 of 4K, which is 12. This is just to break down, it is 2 to the power 12. So this is equal to 12. That means number of bits in page number is 32 minus 12 equals 20. Now let's come to the business. Our virtual memory size, virtual memory address was given this, right? Oh, no, not this one. This one. So this essentially means that, so let's write it down. This is 0, 8A, 2, 9, 8, 5B1. Our number of bits in page number is 20, which means like it is a 5 hex digit towards the MSB side. So this is like 20. It is 5 hex digit, so it would be like 1, 2, 3, 4, 5, like this part. This part is your page number, and the other part, which is like 12 bit, which is like 3 hex number, 4 bit each, right? So this part is your page index. Now you have already given a map this to this 8A298. If this map was not given, this problem cannot be solved. If such a case arises, you should answer, okay, this cannot be solved for this reason, because I don't know that this map is not given, right? So this is my virtual address. This is my virtual address. And my physical address, that means it's going to be 0, 5BC81. That is from this map, okay? And then followed by the page index, 5B1. Now it comes down to the breaking of that bit pattern into different bits. So just to save my time, I can give you the answer here. So we basically make the bit pattern, 32-bit pattern of this, and we can actually have, okay, let me see, normal caption. Okay, so we basically do expand this bit pattern, 32-bit, then break it up into 10 bits block index, then cache line index, 8-bit, and rest of them are tag. And then we convert each of these bit pattern into corresponding hex. And that's what our answer should be given like that. Okay, don't leave it with a bit pattern way. Okay, that won't carry any point. You must need to show me answer with a hex, corresponding hex values. All right, question. Okay, let's take a 5-minute break and we'll be back. So 5-minute break. Okay, let's get back to our business. One thing I would like to share with you is this final exam review topic. So if you in your canvas there is one discussion topic called final exam review, and please go through that. It has this special meeting on the final day to give me a call if you have a confusion, doubt about your question, and etc. etc. It has an exam structure, and there will be this link to the final practice final exam as well. And next day we'll do this topic reviews. Please make sure you put your choice of topic that you want me to elaborate, discuss, or anything like that nature, so that I be better prepared for the discussion on that class. Okay, on the final. All right. Next is quiz time, pop quiz time. Please go to your canvas and see there is a pop quiz number 10 available for you. Hit yes once you are ready to enter the passcode. Okay, 23 of 30. Uh, okay, let me share the passcode. False. Here is the, here it go. Test wet. You have any concern?
Yeah, Professor, there are no input field for my question number two.
Question number 2 has what?
There's no input field for my question number
Oh,
two.
please send me an email. Yeah, some
Okay.
Canvas has some issues with this quizzes. Yeah,
Okay,
send me an
sure.
email.
Thank you.
Now, Professor, question 5 doesn't have a way to answer it.
Yeah, please send me email. I'll check. Okay, I think for most of you, time is up. Before we go for tonight, let me share one more thing with you about the SOTE Solet. There is an assignment, blank assignment for you on the SOTE Solet, that review, uh, but it is being like, it is a bonus grade for you guys, and it is a class bonus grade. So far, for example, right, you in 147 has 23% to fill up on the response rate. So far you have earned 2.3 out of 10. Okay, so as more people participate in that, um, in that uh, um, in that survey, this will go up. For example, like my other class has 44% responses so far, so they have earned so far 4.4 out of 10 as a bonus point. That's a bonus mark. So please make sure you complete your part for your class whole grade 2 up on this. All right. So saying that, maybe we can stop tonight if we don't have any other question.
Professor, I got a question.
Yes.
So the extra points that you're mentioning, what category do they go into?
Those go into the bonus category.
Oh, okay, bonus cat. Okay, and another question: do you know when Project 3 might be graded, even though it's a stretch? I know.
Definitely not before the final.
Okay, that works.
All right, then good night, everybody, and see you on Thursday. Please make sure you put your review